Hi, my name is Valentin Herz and this is my presentation for the ACS meeting in San Diego in March 2016. I am working on arylboranes. Most organic chemists think of arylboranes as starting materials for Suzuki-Miura cross-coupling reactions. In these reactions, the boron-carbon bond is cleaved and a new carbon-carbon bond is formed. The labile nature of the boron-carbon bond is therefore an advantage for cross-coupling reactions, but it poses a major challenge if you want to synthesize and investigate triarylboranes. With the aim to preserve all boron-carbon bonds, let's take a closer look at the main mechanism of degradation. At first, an adduct between the Lewis-basic arylborane and a nucleophile is formed. In the second step, the tetra-coordinated boron atom loses one of its substituents. In order to prevent degradation, it is sufficient to prevent any adduct formation in the first place. Bulky substituents like mesitol offer enough steric protection, and both triarylboranes shown here can be handled under ambient conditions. In the case of the compound on the right-hand side, two of the aromatic substituents are connected. This leads to a perfect alignment of the empty p orbital on the boron atom with the pi systems of the non-mesitol substituents. During my PhD project, I investigated the influence of this special structural motif on the optoelectronic properties of polycyclic aromatic hydrocarbons. It became apparent that the boron atom has a profound impact on the fluorescence properties as well as the electrochemical behavior of these compounds. In this representative example, introduction of one boron bridge in a fjord region of dibenzocrucene shifts the emission wavelengths from near UV into the blue region of the visible spectrum. At the same time, the fluorescence efficiency is increased from 19 to 70%. The impact of the boron atom on the electrochemical properties is also remarkable. If a cyclic voltammetry experiment is performed on the parent compound dibenzocrucene, no reversible redox transitions can be observed. In contrast, the cyclic voltammetry of the boron bridge molecule shown here reveals a reversible reduction and a reversible oxidation event. This means that both the radical cation as well as the radical anion of this compound are persistent in solution. I could even incorporate a second boron atom, which led to an additional, fully reversible reduction event. This rare combination of favorable optoelectronic properties makes boron-containing polycyclic aromatic hydrocarbons very interesting in the context of materials, devices and switches. All the compounds which I will show you on the following slides have been extensively characterized, in most cases even by X-ray crystal structure analysis. But I will omit the details as you can look them up in the two publications mentioned here. Let's have a look at how these arylboranes can be synthesized. Starting from silane precursors, the boron atom can be introduced by a simple silicon-boron exchange reaction with boron tribromide. After addition of a mesitol group for steric protection, these products can be purified by column chromatography. An advantage of the late-stage borylation is that reactions for the extension of the pi system can be performed with the more stable silane precursors. On this slide, I'd like to show you the scope and limitations of this synthesis strategy. The silicon-boron exchange gives excellent yields in most cases. However, if the molecular framework is very rigid, very high temperatures are needed for this reaction, and side reactions cause the yield to drop sharply. The silane precursors on this slide have all been synthesized from the same starting material. Only 3 different types of reactions are needed to build up pi systems of different sizes and shapes. In order to form the central carbon-carbon double bond, I always relied on the Peterson-olefination reaction. This reaction even furnishes the challenging tetra-substituted alkene products in decent yields. It works both with silicon or boron-containing starting materials. There is only a small number of cases in which this reaction fails. In this example on the bottom right corner, both the electrophile and the nucleophile are rather unreactive due to mesomeric effects. If one of the reactants is exchanged against a more reactive one, the Peterson olefination again gives the expected product. For the expansion of the PAH system, I employed two different reactions. Terminal alkane substituents can be incorporated into the molecular scaffold by ruthenium-catalyzed benzanylation. In the second example, whole C6 rings can be added to the planar framework by a stilbene-type photocyclization. Both reactions can be performed on silicon as well as boron-containing substrates. If the boron atom is already in place, one can even synthesize the compound in the bottom right corner, which was not accessible by late-stage silicon-boron exchange. I will now briefly summarize the chemical properties of my triaryl boranes. All these products can be handled and stored under ambient conditions. They can be employed in cross-coupling reactions, such as Stille or Sonogashira type reactions, but they are obviously not stable under Suzuki-Miyaura conditions. Extremely Lewis-basic reagents were used in the synthesis without any side reactions. The compounds are even moderately stable under acidic and oxidizing conditions. In this boron and sulfur containing molecule, the sulfur atom was oxidized with metachloropyrbenzoic acid, although the yield was not very high. I'd like to conclude my presentation with two examples which I find very intriguing. I synthesized this bipolar boron and nitrogen containing molecule and observed a strong charge transfer character in the excited state. This results in a pronounced solvatochromic behavior. The fluorescence color of this compound is blue in cyclohexane, red in acetonitrile, and can be every color in between depending on the solvent polarity. In all the solvents, a very high fluorescence quantum yield was observed. On this slide, I'd like to show you a colorimetry experiment with this molecule featuring two boron atoms. The UV-Vis absorption spectrum, drawn in green, corresponds to a solution of the neutral compound. If 1 electron per molecule is injected into the solution, the absorption changes to the spectrum drawn in blue. As a second electron per molecule was added, the red spectrum was recorded. These processes are fully reversible, which means that both the radical cation and the dianion are stable in solution for a long time. I hope I have sparked your interest in boron-containing polycyclic aromatic hydrocarbons, and I'd like to thank you for listening.